Hey there, and today we'll be exploring the TNNs and ChatGPT foundations and how do they work, explained in simple terms by unpacking mysterious things with A Z. So basically, word embedding. Before we begin, in this video we will be learning about the topics as about what do you call? Yeah, what I said before, like we're going to be learning about the TNNs and ChatGPT's foundation. So before we dive into that, we first need to look at word embedding, which is a key part of neural networks and ChatGPT. ChatGPT uses this to have general context of the question and to provide accurate responses. So basically, words or tokens are converted into numerical representations because neural networks work with numbers, not text. This is important to learn because neural networks do not use text; they use words. Well, I mean they have numerical representations, but still, word embedding involves assigning a unique vector of numbers to each token in vocabulary. So it kind of varies between the AI models I think you use, but relatively they have the same rule. They have your unique tokens for each word and each letter as well. The same embedding is reused for all tokens embedding network, making it efficient and flexible for variable sentence lengths. So basically, this is to simplify things and not make things too complicated, and so that you do not make your brain hurt. Positional encoding. Positional encoding is a mechanism to preserve order since neural networks inherently process inputs without understanding sequence. A sequence of sine and cosine waves generate unique values for each position in the sentence. So that does not get confused. Just like, for example, let's take the example of generating something like radio waves. You call, right? You call somebody, and then after that, you wonder, like, why, if these radio waves, they use radio waves, then why don't you pick up somebody else's calls? Well, that's because they assign you a unique radio wave length. Same thing over here, it generates unique values. Adding these positional values to word embeddings ensures the transformer can differentiate identical words in different positions or contexts. So over here we can have a little diagram over here saying class token, and over here feature tokens, and we have D over here reshape, H W F, and we reshape it to position encodings. Okay, so basically it's a simple diagram explaining all of this. If you can check it out more if you want. Self attention. Self attention calculates how words in a sentence relate to each other by measuring similarity scores. These scores are computed using a dot product of query and key vectors derived from each word. Scores are scaled and passed to a softmax function to create weighted importance values, ensuring focus on relevant words. So over here we have the encoder one. So basically, we first have the positional encoding times one. So we first pipes it to the self attention, then to the add and normalize, then to the feed forward, and then go add to normalize. It can as well takes the root to add and normalize and just gives the feed forward. Encoder and decoder architecture. A transformer is divided into two main components, which are encoder, which converts the input text into an encoded representation, capturing the meaning and relationships. Decoder, which processes the encoded input and generates the output text, maintaining alignment with the input meaning. So basically, just think that encoder, just like computers, the encoder goes into something that the large language model can basically understand. It works like that. For example, you're programming something, and then after that, your coding is basically like you encode, right? So basically, that's exactly what. So basically, the code encodes it to the language that computers can understand, which is zeros and ones. A decoder does the opposite job. Like for example, let's say writing zeros and ones only can be too complicated and time lengthy. So that's why this is decoding into text that you can actually code with. This is how these two kind of work. Training with back propagation. Weights in the transformer are initialized randomly and optimized during training using back propagation. Back propagation adjusts weights by iteratively by minimizing the error between the predictive and actual outputs. Example training involves feeding known English and Spanish sentence pairs with the model learning optimal weight for accurate translations. So basically, this just breaks the rule. So basically, usually back propagation is going backwards, okay? But usually, traditional approaches say that you can only go forwards with this. But back propagation can help neural networks adjust weight and minimize error as well. And so you can also learn if you combine it with AI as well. Residual connections. Residual connections allows information to bypass layers, helping the network retain essential data from earlier stages. Residual connections allow information to bypass layers, helping the network retain essential data from earlier stages. So basically, just like now that we don't need video call, we don't need CDs to go directly, and we don't need to go physical. We can buy. Let's say that. Let's just take example of roads. So basically, traditionally, that you would be going directly through the traffic of the congested roads and that. But then then soon bypasses were invented, so you could bypass it as well. You could bypass the cities and bypass the traffic as well. You don't need to go to the crowded city roads. While self-attention focuses on relationships between words, the pseudo connection ensures the original word embeddings and positional encodings are not lost. Parallel processing. Transformers perform computations for all tokens in a sentence simultaneously, unlike traditional models that process words sequentially. So basically, an example for this, we could say quantum computers and traditional computers. Transformers could be the quantum computers. We can perform computations at and for all the tokens and centers simultaneously, just like quantum computers can analyze all the parts. Like for example, let's take a maze example. All the possible parts together simultaneously, not just one by one, which can improve efficiency drastically depending on the skill of the maze or the problem. This is achieved, and I'm sorry, and let's also think about the traditional models. The traditional models are the computers, which can only be zero or one. Quantum computers can be zero or one at the same time, which drastically improves processing power and time, and it drastically reduces times to solve equations as well. This is achieved through parallelization in operations like calculating word embeddings, positional encodings, and self-attention values. Example, for the sentence let's go, embeddings, positional codings, and attention calculations for both words are computed at once. So basically over here we have a little diagram saying that if A fails and B fails, then system fails. Okay, so P equals to the failure probability. So we have the PEF, which equals to P, a variable of A times the other variable. Or if or B fails, then system fails. So basically, this is a little bit less things because it basically only one is to film. Okay, so in this, for example, only one. If only one goes, then the system does not collapse. But but in this case, uh, if only one, then the whole system fails. If only one fails, then the whole system fails.